Hello and welcome to Rotary Rocketry. Today will be my second attempt at building and testing Dan Pollino's K500 PVC case sugar fuel rocket motor. Great news! We now have Rotary Rocketry t-shirts available. Check them out in our shop. There's a variety of different logos and graphics available. It's a great way to support the channel, and you get a nice t-shirt. This motor was developed by Dan Pollino, and we're going to be following the instructions in his book, I Still Have All My Fingers. Now, in our previous video, we did a complete step-by-step build of this motor. Unfortunately, the ground test didn't end very well. If you want to take a look at that video, I'll put a link at the end of this video, and there'll also be a link down in the description. Now, I think I know what I did wrong in the previous build, so we're going to be trying to correct those errors today, and hopefully we end up with a successful motor. Let's go build it. Now, I'm not going to do a complete step-by-step tutorial build like I did in the previous video for this motor because, well, that one failed, and really at this point it's more about can we get this motor to succeed. So in today's video I'm really going to focus on the changes that we're going to make between this build and the previous build. I'm also going to take some time to talk about some of the fantastic comments that were left in the previous build video because I think some of them are really important to the build and some people had some really good ideas. So we'll talk about those as we get to them. So speaking of comments, there were definitely some comments regarding the safety of PVC for a rocket motor. So let's take a moment to talk about the hazards and safety about PVC casings for rocket motors. Now there's hazards associated with amateur rocketry in general, and there's even more hazards if you're making your own motors and your own fuel, but there are specific hazards with making PVC motors. You see, if a PVC motor explodes, the PVC blows apart into small, sharp little bits, and that could be very dangerous if anybody is nearby. So how do you protect yourself against that? Well, the main protection there is going to be distance. You need to be far away from these when you're testing them. So my general rule is 300 feet or 100 meters. It's generally a safe distance. Even if pieces fly further than that, they're going to lose their velocity pretty quick because they're small and lightweight pieces. Now, we also use the vehicle as a bit of a shield when we're testing motors like this. And it's not just as simple as standing on the other side of the vehicle. It's a little bit more than that. And I'll show you a little bit more of that in detail when we go out to actually test this motor. Now there's plenty of other safety procedures that you should have in place for amateur rocketry or motor testing. For instance, I use a remote control ignition system, and when I'm connecting the receiver to the igniter on the motor, I know exactly where the remote control is located in the vehicle, and nobody is near it or holding it, so there's no chance of it being accidentally pressed while I'm connecting the igniter. That's just one example. Now the motor we're going to be building today is not a beginner's motor. This is a pretty advanced motor, pretty powerful motor. And if you're going to be getting into homemade motors and homemade fuel, this really isn't a starting point. You should be starting with something a little bit smaller and a little bit simpler and certainly a little bit less powerful than this. Now, just like in the previous build for this motor, we're going to be following Dan Pollino's instructions very closely from his book, I Still Have All My Fingers. Now I've got all the stuff laid out here that we're going to need. A couple things are already done because we've already built this motor before. I've already got the core rod alignment tool. The core rod is already built. I've got my wide mouth funnel that we built in the last video. So the first thing that we need to make is the nozzle. So I've got the template attached to the 2-inch PVC pipe. We have to drill those 8 holes. In the previous video, we just used a high-speed drill bit to do that, and that was a little bit of a nightmare because the high-speed drill bit bites into the PVC very violently. We actually broke the PVC pipe at one point and had to start that piece over. Now, a couple people commented, why didn't I just use the step drill that I had shown in the video earlier? And to be honest, it just never really occurred to me to use that. Now in Dan's instructions, he was using a Forstner drill bit that looks like this. I didn't have this in the previous video, but it was only about $9 at the hardware store, so I figured it'd be worth a try. This actually works amazingly well in PVC. I'm going to drill one hole in real time here so you can see just how well this works. It goes right through and the hole is super clean. I cut that piece down to size and that came out absolutely perfect. So we're ready to glue that into the coupling. And now I'll make the divergent cone. Tape that closed, and then we can just simply tape the entire cone so that it's waterproof. All right, so now we're at the first point where we're going to make a change to how we're going to build this motor compared to how we built it before. I have here the retaining bolt template. We did not use this last time. And I have these 4 little brass inserts. I'll show you a close-up of these. Now these inserts go into the nozzle, and these are used so that you can bolt the motor to the rocket. Now we didn't put those in the last one because it was a test motor, so there was no reason to have any mounting points to mount it into a rocket. But one of my viewers made a really interesting comment, so let's go over that a little bit. So the viewer's comment was about compression, and specifically compression of the PVC pipe. You see, when we test these motors on the test stand, they're upside down, so the thrust is pointed upwards and the motor is simply pushing down into a steel plate. So at the moment when we need the PVC to be its strongest, we're exerting an extra force onto it by actually trying to compress it downwards. Now, I had originally thought that in Dan's design, his motor was pushing against a bulkhead inside the rocket. Well, I went back and I looked at the documentation, and it was a little difficult to tell, but it did look to me like the motor had a centering pin at the top that went into the bulkhead, but then for the final installation, the motor was pulled back a little bit from the bulkhead so that the screws could be secured in around the bottom of the nozzle, meaning that the motor was not pushing against anything in the rocket. It was simply attached by these 4 screws down at the nozzle. So there's definitely some merit to the idea that if we're testing this upside down and compressing the PVC, we're going to be adding an extra force to that PVC that wouldn't normally be there during Dan's launches when he was originally using this motor. So we want to simulate his environment as closely as possible so we're not adding any extra stress. So that's why I'm going to put those 4 inserts in here. And then when we make the test stand, I'm going to make this so that the motor sits in the test stand, is screwed in as if it was screwed into a rocket, and the bottom of the motor will not be pushing against anything. It will just be centered but floating up in the air. So let's go ahead and install those inserts. I've got that template installed, and it says to drill those holes 5/16 of an inch, and the instructions also say to use a vise so that we can be sure that we get a nice straight hole for that insert. And then using a vise, we'll press those in one at a time. And now we'll just install some 1/4-inch screws into each one of those inserts. We'll screw that all the way in so that it completely fills the insert. That way when we pour anchoring cement into here, it won't fill up or pour out of the threaded insert holes. Here I have the nozzle washer. I decided to purchase the exact nozzle washer that Dan was using. I also have the nozzle throat template that fits inside of that washer. It's a little tight, but it does fit in there. There we go. So we take the divergent cone, put that into the nozzle. We put the washer down onto the cone, kind of get it leveled up, and then we put that template inside of the washer. And we're ready to pour the anchoring cement for the nozzle. There's the finished nozzle, and I've cut the PVC casing to length, and we just need to glue those together. Now in the previous video, we had some comments about making some changes to the outer casing to make it stronger. So let's take a look at a couple of those comments. So this motor casing is made from Schedule 40 PVC pipe. There were a couple of recommendations to switch to Schedule 80 piping, which is much thicker wall. There was another recommendation to wrap the entire finished motor in fiberglass. I'm guessing he meant fiberglass fabric with resin, so you'd end up with a hard shell around the entire motor for reinforcing. And another comment just to switch to aluminum altogether. Now those are all good comments, and they would certainly make for a stronger motor casing, but bear in mind, I'm not developing my own motor here. I'm using Dan Pollino's instructions, and I'm trying to build this motor using the same materials and same techniques that he did on his builds. So I'm not really looking to make any kind of structural or physical changes to the motor. So that's why we're staying with Schedule 40 PVC. Now before we make the fuel for the motor, we're going to make the igniter. That way we can install the igniter onto the fuel as soon as we pull the coring rod out. So I've got everything here. I have some of the powdered fuel mixture already left over from the previous build. Now we're just about ready to make the fuel for this motor. Now I'm pretty sure this is where things went wrong in the previous build. I'm very confident that I overheated the fuel in the last video, and that may have led to the explosion of the motor on the test stand. So we're going to change the cooking process a little bit. So let's go ahead and talk about the changes we're going to make and some of the comments from the previous video. Now in Dan's instructions, he says to turn the wok to its highest setting to cook the fuel. And I think that's where things went wrong. The surface of the wok gets extremely hot. And I'm sure Dan had a very good system where he knew exactly what he was doing and exactly when to stop the wok and pour the fuel. But since we've never done this before, or only once before, and it failed, it's a little tricky to get the system down exactly perfect. So instead, we're going to start by cooking the fuel at the lowest setting on the wok and just slowly raise the temperature of the wok until we get the fuel to where we want it to be. Now the target temperature is 210 degrees Fahrenheit. But what we're going to do is we're going to cook the fuel until we reach a temperature of 200 degrees Fahrenheit and then turn off the wok. Because the wok will still be very hot, so the fuel will continue to heat up while the wok starts to cool down. And hopefully we'll end up with a fuel somewhere between 200 and 210 degrees Fahrenheit. Now a couple of viewers in the last video recommended using a double boiler for cooking the fuel, which, to be perfectly honest, I think is an amazing idea. It's a spectacular idea. The maximum temperature you could get would be 212 degrees, and our target temperature is 210 degrees, so we're right in the range of where we would want to be. And the double boiler would prevent any kind of burning or scorching of the sugars. So it's a spectacular idea. Now, I say it's a spectacular idea, but we're not going to be doing it. The reason is I bought this wok especially for this project, and this is the technique that Dan was using to make his fuel. So in theory, we should be able to make the fuel exactly the same as Dan in the electric wok. Now I guess if we do this a third time because this for some reason fails, the double boiler idea is always a possibility. And the last thing we have here is the coring rod. Now in the last build, the coring rod got stuck in the motor pretty hard. We did manage to get it out without damaging the fuel, but it was in there very hard. Now hopefully this will be a little easier to get out if the fuel is a little bit softer like it's supposed to be, because we're going to cook it to that lower temperature. But a couple of people recommended polishing the rod or sanding it with a much finer sandpaper. So I've got some 1200 grit sandpaper. I'll give this a rub down with the 1200 grit, and hopefully that extra smooth surface will make it easier to get it out. If it does get stuck, we do always have our little extraction tool that I built to get it out the last time, so we'll use that if we have to. All right, we're going to let that cool for 3 hours and attempt to pull out the core rod.
3 hours later.
All right, let's give it a try. Wow, absolutely no resistance at all. So I don't know if that was just the change in the fuel or the polishing of the rod with the fine sandpaper, but that was fantastic. Now I have some sample pieces of the fuel that we got here that we just scraped out of the pan. Now, the fuel is supposed to be a little bit flexible, a little bit pliable, not rock hard. So it is interesting that it is very flexible. This is much more similar to what I expected to have for a final result. So hopefully we've got it right this time. I cut the motor down to its finished size, and I discovered a little bit of a problem. You see, the fuel is only down from the top of the PVC about 1/2 inch. And that's a problem because we still need to install the igniter on top of the fuel, and then we need room to bury that in the smoke element epoxy, and there's just no room to do that. So why does it appear that we have more fuel than we're supposed to have? Well, not really completely sure. I used the exact same quantity of ingredients that I used in the previous build, right down to the 1/10 of a gram, and it's the exact quantities that Dan specifies in his instructions. And in the last build, that was definitely a little bit lower. Now, it could have something to do with that cooking temperature, causing the fuel to shrink a little bit more when it's cooked to a higher temperature. I looked at the illustrations in the instructions, and it looks like the fuel should be down about 2 inches from the top. That seems about right because that would give us room to install the igniter and then plenty of room to install the smoke element around that and bury it in place. So the nice thing is this fuel is a little bit kind of soft and squishy because of that lower cooking temperature, so that's good. So I'm going to use a screwdriver, maybe some other tools here to just kind of chip away at that fuel, and we'll get it so that it's about 2 inches down from the top. And there it is. I've got it down about 2 inches down from the top, and I've got a nice flat surface where that igniter can sit. The igniter's installed. Now, just so you see, this is the amount of fuel that we took out. It's quite a bit. So if you're wondering, what do you do with leftover sugar fuel? Well, there's two things. One, it's water soluble. So if you just soak this in water, it'll completely dissolve. The other thing you can do with it is a little more fun. Next, I'll make the smoke element, and that's just a mixture of 2-part epoxy and potassium nitrate. We just need to let that epoxy harden for a couple of hours, and then we'll be ready to finish the motor. Next, I'll install the cap. And then I'll glue the sleeve in place and wipe off the excess. And the final step to finishing this motor is to fill the airspace under the cap with anchoring cement. Alright, so this motor is finished. Now we just need to work on the test stand. And as I said earlier in the video, we want to hold the motor into the test stand similar to how it would be held in a rocket. So I've got this length of 3-inch PVC pipe. It's a little bit longer than the total length of the motor. And on the top here, I've drilled 4 small holes. Those holes line up with the 4 mounting holes in the nozzle of the motor. That will allow us to slide this down into the pipe and use 4 screws to bolt the pipe to the motor. Now the motor outside diameter is a little bit smaller than the inside diameter of this 3-inch pipe. So I've got these cardboard rings that will fit inside of this pipe, and that will allow the motor to fit in nice and snug so that we can tighten those bolts down. And then on the bottom, I've got another ring that will go in so that the bottom of the motor won't move around inside the pipe during the test. So I'll go ahead and get that motor installed. So as I said earlier, I was going to show you how we use the vehicle as a shield when we're testing motors. So once we get the motor hooked up to the ignition system, we're going to drive the vehicle a couple hundred feet away, and then we open up both of the doors on the side of the vehicle, and we stand in between the doors like this. Now this door is going to offer a lot of protection as far as debris, and we can also look through the glass to see the event. Now, if there's any danger of anything coming our way, if we feel that there's any further danger, just simply one step and we're in the vehicle. So my point is, when you're developing, building, and testing homemade motors, you really need to think about safety throughout the entire process. Make a plan first so that when something goes wrong, you already have that plan in place. Let's go hook our motor up. All right, that was absolutely amazing. Now, to be honest, I kind of expected it to explode, so that was fantastic. Huge amount of thrust. So after the burn, we got a lot of smoke dumping out. That was the smoke element burning that would leave the smoke trail behind the rocket, so that was fantastic. We're going to take this back to the shop and get it out of this casing and take a look at how the motor held up inside. Now is probably a great time to remind you, if you're not subscribed to the channel, please consider hitting that subscribe button. And hey, now's a great time to hit that like button. We really appreciate it. And don't forget, Rotary Rocketry t-shirts are available in our shop. Check it out. Now, we had 3 cameras out there for that test. Unfortunately, one of the cameras got turned off just before the motor was ignited. The second camera kind of got blown to the side a little bit because it was really windy out, but it still caught the test. Let me show you that footage. I've unbolted the motor from the test casing. Let's see how that held up. So in general, the motor is in really good shape. Down here where the smoke element was burning, we do have some deformation of the PVC pipe as well as that coupling, but we don't have any blow through, so that's good. The coupling did its job as far as providing a second layer of PVC there. So that was expected just because of the extreme heat of the smoke element. So overall, it held together just fine. Now up here at the nozzle end, you really can't see in there just because it's black and just covered in soot, but we do have some deterioration of the anchoring cement divergent cone. Again, that's to be expected just because of the amount of force and thrust from this motor. So after the washer, we still have about 1/2 to 3/4 of an inch of the divergent cone in perfect shape. The rest of it just got completely destroyed because it gets thinner as it gets closer towards the end here, and that just disintegrates. So that held up just fine, and I'm really impressed, especially since, to be honest, I kind of expected this to explode. So that little change to the fuel and possibly the change to how we were holding the motor into the test stand, those two changes together ended up in a perfectly successful motor. So I'm really happy about that. Now that we've successfully built and tested Dan Pollino's K500 motor, it's time to move on to the next step, and that's to build a rocket that can hold this giant motor. I'll be working on that project and we'll be back real soon. Thanks for watching. We'll see you next time.